Good morning. My name is Armando Ramalho, and I'm here to present the article Simulation of Crack Growth in Residual Stress Fields of Pre-Fatigued T-welded Joints Repaired by Tungsten Inert Gas, a 3D approach. Here is a brief outline of my presentation. Currently, due to economic and environmental constraints, the use of welded structures beyond their design lives is frequent. So that this situation is not catastrophic, an extra effort should be paid to inspection, monitoring, and rehabilitation of damaged details. The growth of fatigue cracks at the weld toe of the joints is one of the main causes of failure of welded structures. The use of improvement techniques in welded joints as a repair technique has been reported by several authors. The TIG remelting is one of the most efficient repair techniques of pre-cracked welded joints. Frequently, the efficiency of TIG remelting repair is evaluated using the simulation of crack growth at the weld toe through numerical finite element models. The virtual crack closure technique allows to consider the effect of stress field in the determination of stress intensity factors. In the study is presented a 3D finite element method model that, using VCCT, allows the fatigue life evaluation of T-welded joints repaired by TIG remelting. The base material was a medium-strength steel in the form of plates with 12.5 mm of thickness. The welds were made by covered electrode process with weld metal in overmatching condition. T-joints weld specimens were produced from the main plates with low penetration fillet welded with an attachment of equal thickness. The T-joints were loaded in 3-point bending fatigue until the generation of visible cracks at the weld toe. TIG repair was performed at the weld toe. It was used the numerical model developed in previous work to simulate the TIG dressing process at the weld toe of an as-welded T-joint. The thermomechanical characterization of the steel was obtained in previous work. A 3D transient nonlinear heat flow finite element analysis was carried out in MSC Mark software. Adiabatic boundary conditions were considered in the symmetry plan of the joint, and in all the other surface, convective radiative conditions were used. The heat generated by the arc welding was inputted using the doubly ellipsoid heat source model. The estimated residual stresses were compared with the experimental results. This numerical model was validated by the good agreement observed between the numerical predictions and the experimental values obtained by X-ray diffraction and hole drilling technique. The estimated residual stress field was computed as initial conditions in the crack growth process. The initial mesh is generated in MSC pattern with tetrahedral full integration linear elements. In this initial mesh is generated a semi-elliptical pre-existing crack. For the TRD specimen, the crack is superficial, and for the TR3 specimen, the crack is embedded. This initial crack is generated in MSC Mark software by a faceted surface through a remeshing process. This model will be subjected to 3-point bending fatigue with a pulsating nominal load corresponding to a stress range at the weld toe of 350 MPa for the TRD specimen and 200 MPa for the TR3 specimen in two different initial conditions. with the initial stress field previously estimated without initial stress field. The crack propagation were evaluated using the integration of Paris-Edogan law. The material propagation constant were obtained in previous work. The stress intensity factors were obtained using the 3D DCCT technique implemented in MES3 software. It was used a maximum crack growth increment of 1.1 millimeters. In Table 1 are presented the estimated lives of the TRD specimen, where the T melting conduces to the integral repair of pre-existing shallow cracks. N estimated and N-line estimated correspond respectively to the lives obtained at the simulations with and without the initial conditions of stress field generated by TIG dressing. Delta sigma correspond to the nominal stress at the well toe. Here are presented the fatigue results for the TRD specimen. In Table 2 are presented the same results for the TR3 specimen, where the TIG remelting conduces to poor repair of pre-existing deeper fatigue crack. The TIG remelting produces an approximately semi-elliptic embedded crack. Here are presented the fatigue results for the TR3 specimen. The video shows the evolution of the crack front along the simulation. From the presented results, we can draw the following considerations. The estimated lives for the TRD specimen with and without initial stress fields present a deviation from the experimental one of 9% and 15% respectively. The estimated lives for the TR3 specimen with and without initial stress fields both present a deviation of 11% to the experimental one, the first by excess and the second by default. The numerical model produces a good estimation of the experimental life of the specimens. The estimated geometry of the final configuration of the crack is close to that what occurs in the specimens. The compression stress field generated by TIG dressing causes a delay in crack growth. Conclusions. The developed 3D finite element model reveals to be effective to predict the growth of cracks at the well toe of a T-joint. The developed 3D finite element model reveals to be effective to evaluate the influence of residual stresses generated by the TIG remelting process at the well toe on crack propagation speed. The developed 3D finite element model reveals to be effective to predict the growth of embedded cracks resulting from poor repairs. Here are the main references cited in this presentation. Thank you for your attention.